Everyone, please respond to the polls quickly. That's good, Abdulhadi. Does that mean you got 50 out of 50? Yeah, but please don't do that. Don't look at the marking scheme while you're doing the paper. That'll hurt you otherwise. In the exam as well, you'll have this urge to just look at the marking scheme every few minutes after every single question. You cannot afford that. Can everyone please respond to the polls if you haven't already? All right, so we're doing these two papers today, June 2023, paper 4-1, and June 2023, paper 4-3. We will be doing difficult questions from these two papers, inshallah. Okay, all right, so we have around 3 questions from the first paper that you guys are asking about, and pretty much the same number from the other paper as well. Okay. Let's get started. So we'll start with the 4-1, paper 4-1. You're asking about questions 5, 6, and 7 from this paper. So basically the last 3 questions. Let's look at them. Last 3 questions of this paper. Let's see how we will deal with them. This is May 23, paper 4, variant 1. Okay, question number 2. Question number 1, 2, 3. All right, so you're fine with the first 4 questions, and now this is the one that you're asking about, question number 5. Why? That's like a forces in equilibrium question. What's the problem with this? Why question number 5? Okay, let's try this. It says 4 coplanar forces act at a point. The magnitudes of the forces are F Newton, 10 Newton, 50 Newton, and 40 Newton. The directions are shown on the directions of the forces are as shown in the diagram. Given that the forces are in equilibrium, okay, in the first part, the forces are in equilibrium. That means the opposite forces have to be equal to each other. Forces acting towards right, they should equal forces acting towards left. Forces acting upwards, they should be equal to forces acting downwards, right? Let's first of all resolve the forces. 10 is acting to the right. No one has voted for 5? Oh, I'm sorry. So I was looking at the other paper. Okay, sorry about this. So I was just wondering why 5. Okay, so I was looking at 4-3. Question number 4. Okay, so question number 4 from this paper. That's the first question that we have from this paper. Yeah, sorry, 4, 6, and 7 from this paper, and then 5, 6, 7 from the other paper. All right. Question 4. It says, yeah, sorry about that. I was looking at the other poll, 4-3. Achha. Question number 4. The velocity of a particle at time t seconds after leaving a fixed point O is v meters per second. The diagram shows a velocity time graph which models the motion of the particle. The graph consists of 5 straight lines. Okay, the particle accelerates to a speed of 0.9 meters per second initially, and it does that in a period of 3 seconds. You can see that on the diagram as well. Then it travels at constant speed for 6 seconds. Okay, it comes to rest 1 second later. The particle then moves back and returns to rest at O at time t seconds. Now, this is an important point. It comes to rest at O. It started from O. And it's also ending at O. So it has reached the same point that it started from. Okay. So that means its displacement is going to be 0, or the distance traveled in one direction, that will be equal to the distance traveled in the other direction. Now, in the first part, they're saying, find the distance traveled by the particle in the first 10 seconds of its motion. Now, it's a velocity time graph. In a velocity time graph, displacement is given by the area under the graph. Now, this is all positive, so we can just find the area under this graph, and that will give us that displacement. It's a trapezium. How do you find area of a trapezium? Half into sum of parallel sides into height. Parallel sides are 6 and 10. So we say 6 plus 10 times the height. Height is 0.9. This time 0.9. And that will give us the result. You can see what that is. 8 into 0.9, that will be 7.2. Yeah, thank you. That's part A. They have given so much space for that. Okay. Given that t is equal to 12, find the minimum velocity of the particle. Capital T, this value is 12. That's what they're saying. Find the minimum velocity. What minimum velocity? That's this value here. We want to find the value of v. Now, how do we do that? The particle started from O, it returned to O. That means whatever distance it traveled in one direction, it's traveling the same distance in the other direction. That means the area of this triangle should also be 7.2. How do you find area of this triangle? We can use half into base into height for this. What's the base? We can take this side as the base. Its length is 2 units, right? 10 to 12, that is 2. What about the height? Height is perpendicular to the base. This is the height. So what's the area of the triangle? Height, we can say that is v, although the value of v will be negative at the end. Let's actually call this something else. Let's just call this x or h. Let's find the height of this triangle. Half into base, which is 2 into height, that should equal 7.2, right? Because this area of the triangle should also be 7.2 if it's returning back to the same point again. Okay. The particle started from O and it returned to O as well at the end. Right? It started from O and it returned to O. So the point that it started from, it's returning back to that same point. So displacement is 0. So whatever is the displacement in the positive direction, it's the same in the negative direction. Okay. So that gives us that the height of that triangle, that is equal to 7.2. They asked us for the velocity. Velocity is a vector quantity. Velocity is a vector quantity. And this is a negative value here. So we are going to write negative 7.2 here. Okay, don't write positive, it's a velocity. If they had asked for speed, we would write 7.2. Velocity is negative there, we'll say v is equal to negative 7.2, and that's your final answer. Okay. Let's move on. That was the first part. So the second part, now it says, given instead that the greatest speed of the particle is 3 meters per second. That means this is no longer relevant. What they said in part B, t is not equal to 12 anymore. The greatest speed is now 3 meters per second. Find the value of t and hence find the average speed of the particle for the whole motion. Okay, first of all, find the value of t, and they're saying the greatest speed is 3 meters per second. Greatest speed is 3 meters per second. What does that mean? Look at the graph. And on the positive side, you've got 0.9. We don't have 3 there. That means on the negative side, the greatest possible speed is 3. That means the value of v here is going to be negative 3. Okay, so now we know that the height of this triangle, that is 3 units now. And now we have to find the base of the triangle. This is 3, and we have to find the base. Let's call that b, the base. Let's find the value for that. Half into base into height, that equals 7.2. And that will give you the value for b. What does that turn out to be? Value for b, 14.4 divided by 3. What's that? 4.8, I think, right? Base turns out to be 4.8, yeah. 4.8, that's the base. What does that tell you about the value for t? This length is 4.8, so the value of t therefore is going to be 10 plus 4.8, that is 14.8. That's the value of t that we were looking for. Okay, that's this part. So we found the value of t now. Now that we've got the value for t, the next thing that they want us to find out is the average speed for the whole of the motion. Okay, average speed. Average speed is given by total distance over total time taken. We're looking for speed, right? Not average velocity. That's total distance. What's the total distance? The distance traveled in this direction was 7.2. 7.2 in the other direction. The total distance is 14.4. 7.2 plus 7.2 divided by the time taken. What's the total time taken? 14.8. And that will give you the average speed. What does this number turn out to be? 0.97. Is that exact? Exact 0.97? No. If you round off, it has to be three significant figures. So that's 36 over 37. What's the value in decimals? What's the value in decimals? 0.973. Yeah, so if you write 0.97, you can lose 1 mark because of that. That's the average speed that we were looking for. Okay. Achha. Now, how do we know that v is equal to 3 is going to be in that particular time interval? The question says, the minimum velocity of the particle, sorry, here, greatest speed of the particle, greatest speed. Now, this vertical axis represents velocity. Greatest speed could either be on the positive side or could be on the negative side. So what's the highest point of the graph, or what's the lowest point of the graph? This is the highest point of the graph, that's 0.9. That's not 3, we know that. What's the lowest point of the graph? That's this. So that is supposed to be the greatest speed. So that point has to be 3 here. That means that the height is 3. जो initially greatest थी, क्या मतलब उसका?
मतलब इनिशियली वो उस पॉइंट पे जहाँ पे v इज इक्वल टू 7.2 है, उस पॉइंट पे वी हैड द ग्रेटेस्ट स्पीड. तो अब उन्होंने कहा कि गिवन इंस्टेड के ग्रेटेस्ट स्पीड इतनी है, तो मतलब जहाँ पे पहले 7.2 थी ग्रेटेस्ट, तो अब वहाँ पे 3 है.
बिल्कुल ऐसी है. So उसने पहले कहा था कि t की वैल्यू इधर 12 है. उसके corresponding the value of h that we were getting, the value of v that we were getting was negative 7.2. Now t is not 12 anymore. They've fixed the value of v instead, and that's minus 3 now. उसके corresponding फिर हमने t find किया, that's a different value for t. So yes, this 3 is in place of the 7.2 in the previous part. Yes, that's correct. Okay. All right, let's move on to the next one. That was part C of this, and that's it. That's question number 4. Can I move on? Okay, question number 6. That's the next question that we got from this paper. Question number 6. Where is the noise coming from? No, units are not important. In mechanics, you don't have to write units. If you're doing S1 as well, in S1, yes. In representation of data, that's one topic in which units are important. So throughout your A levels, representation of data is one topic where you have to mention units in your working. In mechanics, you just have to be able to understand units correctly. So sometimes they give values in kilo something. That's the only type of question in which you have to take care of the units. Otherwise, you don't necessarily have to write this down. Just write 0.973. That's okay. Okay. You did not understand anything, Abdul Hadi, because you could not hear anything. It was fairly straightforward. What I'll do is I'll be uploading the recording, and you can go through that, because if you go through that whole thing again, that will take some time. Is that okay? I'll upload the recording right away. Is that okay? Yeah. So that was a fairly straightforward question. You can just watch the recording and you understand that. Question number 6. That's the next one that we've got. Okay, question number 6. It says the particles P and Q of mass is 0.2 kilograms and 0.1 kilogram respectively. They are attached to the ends of a light and extensible string. The string passes over a fixed smooth pulley at B, which is attached to two inclined planes. Particle P lies in smooth plane AB, which is inclined at 60 degrees to the horizontal. Particle Q lies on BC, which is inclined at theta degrees to the horizontal. The string is stored and particles move in this direction. So the only important piece of information here was that this is smooth, everything else is given on the diagram. Now in the first part, they're saying it's given that theta is equal to 60 degrees. Theta is equal to 60 degrees. The plane BC is rough. The plane BC is rough. The coefficient of friction between Q and plane BC is 0.7. The particles are released from rest. Determine whether the particles move. Determine whether the particles move. Okay, now how do we think about this? We first of all resolve the forces, right? Resolve the forces. That's good to know, Serena. You have made me lose a bit of focus, but thank you. That's good to know. Weight, what about the weight? Weight is 2 Newton. The weight of Q is 1 Newton. We've got the reaction, that's this, and we've got this reaction here. We've got tensions. There's one tension acting in this direction. There's another tension acting in this direction. Okay. This surface is rough. This surface is rough. Now, this surface is rough. That means there's friction here. Both the angles are 60 degrees. Which one is the heavier object? P is heavier. Now, since P is heavier, P is going to move downwards because the angles are the same, right? Otherwise, you'll have to find components. You can find components of the weight as well. You have the weight component here because they are not telling us in which direction the objects could start moving, right? So we have to figure that out ourselves. In which direction would they start moving? How do you figure that out? Weight of P is 2 Newton. The components of P are the components of this weight are going to be in this direction and in this direction. If this angle is 60 degrees, this is also 60 degrees. So the component along the surface, that is 2 into sine of 60. And for 1 Newton weight, we've got two components, one in this direction, another in this direction. This is going to be 1 sine 60 and the other is going to be 1 cos 60 because in the first part, this angle is 60 degrees. And now we know 2 sine 60 because they're telling us in the first part. They're telling us in the first part. In the first part, theta is 60. Otherwise, we cannot assume that, okay? Achha. Now, 2 sine 60 is greater than 1 sine 60. 2 sine 60 is greater than 1 sine 60. What that means is there is greater force in this direction. So P is going to try and move down the plane and Q is going to try and move up the plane. So what's the direction of friction then? Friction is going to act down the plane like this. These are all the forces that we've got. We've got reaction for P in this direction, reaction for Q in this direction. These are all the forces that we've got. Okay. We don't need reaction for P. You can ignore that as well if you want, because there's no friction on that side. So if you don't want to represent that, that will be okay. There is no problem with that. Okay, now let's equate the opposite forces. The ones acting perpendicular to the surface, they are always going to be equal to each other. Now, along the surface, there could be movement. We have to determine whether there is any movement or not. Okay. Now, how do you do that? We've got two objects. One is P. Let's write P down on the left side here, and the other is Q. What are the forces acting on P and Q? Let's understand them. On P, along the surface, we have 2 sine 60 and T, right? And on Q, we have T here and 1 sine 60 and F here. Now, look at the overall system, in fact. In this case, since we have to determine whether the particles move, and we do not need the values of tension, this is actually one case in which we consider the whole system together. That will make things easier to understand. What do I mean by that? Consider this whole thing as one, right? On the left side, you have 2 sine 60 force applying down the plane. On the right side, you have F plus 1 sine 60 acting down the plane. Let's write them down. On P, we've got this force, 2 sine 60, that's acting in this direction. On Q, we have F plus 1 sine 60 acting, that's acting in this direction. Now, if 2 sine 60 is greater than the maximum possible friction plus 1 sine 60, then P is going to start moving downwards and Q will start moving upwards. If, however, 2 sine 60 is not able to overcome friction plus 1 sine 60, then the particles will not be moving. Okay. Now let's figure out these values first of all. 2 sine 60, what's that? That's just 2 under root 3 over 2. That's under root 3. So on the left side down the plane, we've got this force acting. That's under root 3. On the right side, we've got these two forces acting. Friction, let's consider the maximum possible value of friction and see what that would be. Mu times R plus 1 sine 60. Sine 60 is under root 3 over 2. The value for mu, are we given that? Yes. In the first part, they're saying this is 0.7. 0.7 times the reaction. What's the reaction? Reaction for Q is equal to 1 cos 60. Cos 60 is 0.5. So reaction for Q is 0.5. So we get 0.7 into 0.5 plus under root 3 over 2. Now we can convert them to decimals to be able to compare them. Under root 3, you're saying that is 1.732. 1.216 is the overall result from here. Okay, so 1.216 is what we get here. What does that mean? The force acting in this direction is greater than friction plus 1 sine 60. That is why the system is going to start moving. P will start moving downwards and Q will start moving upwards. Okay, so we say 1.732 is greater than 1.216. So that means this force has overcome both the friction and that weight component. So the particles start moving. So particles do move. Right? Determine whether the particles move. So yes, they do start moving. All right. Are we assuming that there's limiting equilibrium? No, we're not assuming anything. We are finding the maximum possible value of friction. So particles are going to move only if this force in the downward direction is able to overcome both the friction and the weight component acting in the other direction. So what's the maximum possible friction we can have? We are basically considering that. The maximum possible friction is this 0.35 plus the weight component. That combined is less than the force acting on the left side. That means friction cannot stop it from moving. Friction cannot stop it from moving. Can we do it using acceleration? You can do that. In this case, that would work. But what if the particle was not moving? Then that would not work, because in this case, the end result is that P is moving downwards and Q is moving upwards. So even if you were to use Newton's second law of motion, you would get some acceleration, and that will mean that the particles will start moving. But if the particles were not moving, we don't know whether they're moving or not. We only use Newton's second law of motion when we know that the particles are moving. In this case, we're not sure about that. So we're just comparing the forces, comparing this force and this force. If the force acting in that direction was, let's say, 1 Newton, let's suppose, and this was 1.216 Newton, what would happen in that case? What would happen in that case? If this was 1 Newton and this was 1.216, in this case, the particles will remain at rest. It's not that the particle is going to start moving downwards. No. Because in that case, friction would start acting in the opposite direction, and it will not let the particles move in the downward direction. Okay. So the takeaway is, since you have to determine whether the particles are moving or not, you have to consider these two forces separately and then see if that force is able to overcome friction or not. We are not comparing horizontal forces. We're not doing that. We are comparing these forces. Force acting down the plane in this direction, force acting down the plane in the other direction. These are not horizontal. These are the forces acting along the surface. Does that make sense? No problems? Okay, good. Let's move on. Part 2. Now, part B says it's given instead that the plane BC is smooth. Now, the second, this plane on the right side, that's also smooth. That's what they're saying. In this case, the particles are released from rest, and in the subsequent motion, the tension in the string is under root 3 minus 1. Find the magnitude of the acceleration of P as it moves up on the plane and find the value of theta. Now, both planes are smooth. What I'm going to do is I'm just going to copy this diagram. So we don't have to redo this work. You will be annotating using a pencil in your exam so that you can edit anything if you need to. Okay, so we have represented all the forces here already. Now, what has changed? The angle is no longer 60 now. That's just theta. That's what they're saying. The angle is just theta. Okay. So this angle now is theta. Okay, so we're given the value for tension. Find the magnitude of acceleration of P as it moves on the plane and find the value for theta. Now we can apply Newton's second law of motion on both the objects. We've got object P and we've got object Q. Now, since we're talking about tension in this case as well, now we can apply Newton's second law of motion on both the objects separately. In which direction is P going to move? P is going to move down the plane. Q is going to move up the plane. So these are the positive directions for them. What's the positive direction for P? It's 2 sine 60. So we apply Newton's second law of motion. Resultant force equals mass into acceleration. The forward force is 2 sine 60. Backward force is tension. We know the value for tension, that is this under root. Let me have to write it like this first. And then this equals mass into acceleration. Mass is what? You know the mass? 0.2 times A. That's one equation. Now, since the other plane is also smooth now, we can get rid of friction from here as well. That's not going to be there anymore. There's no friction. That means we also don't need this reaction, so we can ignore that as well if we want. What are the forces acting on Q now? Q is moving upwards. The forward force is T for that. Backward force is 1 sine theta. This should equal mass of Q, which is 0.1 times acceleration. Solve these two equations simultaneously. You'll get the values of T and A from this. Okay, what I can do is I can make T the subject from the first equation. That gives me 2 sine 60 minus 0.2 times A. That's 2 under root 3 over 2. That will be under root 3 minus 0. Oh, so I'm sorry, we know the value for T already as well. So that actually makes it much simpler. We know the value of T. What was the value of T? Under root 3 minus 1. Let's just input that. So that's fairly straightforward. Then 2 sine 60 minus the value for T. That's under root 3 minus 1. They have given that value in the question. This value here. That equals 0.2 times A. You'll get the value of A from this. What's that value of A? 5. So we get A equal to 5 from this. Put that in the other equation, and that will give you the value for theta. You can find that. That's the other value. That's 4 marks. That's not that difficult. Once you resolve the force in the first part already, the second part is just using those same forces. Yes, what do we get? The value for theta? It will be sine inverse of under root 3 minus 1 minus 0.5. That will be minus 1.5. Sine inverse of this. What do we get from this? 13.4 degrees. Okay, thank you. Theta is equal to 13.4 degrees. That's what we were looking for. That's the final answer. All right. Okay, let's move on. Question number 7. A car of mass 1200 kilograms is traveling along a straight horizontal road. The power of the car's engine is constant and it's equal to 16 kilowatt. Okay, so mass is 1200 kilograms. And it's going on a straight horizontal road. Power of car's engine is constant. This is car. Its power is 16,000 watt. There's a constant resistance to motion that has a magnitude of 500 Newton. So we have this car going, it has a driving force, it has resistance. That resistance has a value of 500. They're saying find the acceleration of the car at an instant when its speed is 20 meters per second. So how do we think about this? Power is equal to driving force into velocity. Since they're talking about acceleration, the other equation that we'll use would be Newton second of motion. Power is 16,000 watt. 16,000 into driving force into the speed, that is 20. You'll get the value for driving force from here. You can see what that turns out to be. And then forward force is driving force, backward force is 500. That equals mass, which is 1200 times acceleration. The driving force you're saying turns out to be 800. Put that in the other equation, and that will give you the value for acceleration. 800 minus 500 equals 1200 times A. 300 over 1200, that will turn out to be 0.25 meters per second square. That's the acceleration. Right? Fairly straightforward, very standard power question. Yeah, in B part. Yes. And the previous question's B part, yes. So that's what we did. We applied Newton's second law of motion for P and Q separately. And that gave us the result. Okay. Now it says, assuming that the power and the resistance forces remain unchanged, find the steady speed. Steady speed. When it becomes stable, that means acceleration is zero, right? Steady speed means it's like constant speed. Acceleration is zero at that point. Okay, so again, we can say power is equal to driving force into velocity. Power remains constant. That's the same as before. That's 16,000. Resistance is also constant. Now, driving force is not constant. They've not told us that. Let's consider the surface. We've got this car. There's a driving force acting on this car. There's a resistance acting in the backward direction. Apply Newton's second law of motion in this. Resultant force equals mass into acceleration. The forward,
wouldn't it be 500 as well?
500 what? The resistance, yes.
If the
Resistance will be,
resistance is 500, तो driving force भी मतलब 500 ही होनी चाहिए ना?
yes, in this case, it will be 500 because of the steady speed. Since acceleration is zero, when we apply Newton's second law of motion, it turns out to be 500. So you can do it directly as well. So if you understand that when acceleration is zero, then the forward forces and the backward forces, they're supposed to be equal to each other. You can directly write 500 there as well. Or since we always, use these two equations, you can just use them. Forward force is driving force, backward force is 500. That equals mass into acceleration. Since acceleration is zero, that gives you driving force equal to 500. But you can do it directly as well. You don't necessarily have to show working for this. You can directly write 500 here, and that will work. You find the value V from this. What's that? 32. All right, thank you. 32, that's the steady speed that we were looking for. That's part B. Now it says, the car comes to the bottom of a straight hill of length 316 meters, inclined at an angle to the horizontal of sine inverse of 160. Okay, let's draw that. That will make it easier to understand. We've got this straight hill. This angle is theta, and we are given that theta is equal to sine inverse of 1/60. Okay. Sine theta is equal to 1/60. That's what we're given here. Length is 316. The power remains constant at this value. Power is equal to 16,000 watt. Magnitude of the resistance is no longer constant. If the resistance is no longer constant, then that means you cannot use any constant acceleration formulas here. Okay, don't try that because the forces are not constant. When the forces are not constant, then the acceleration is not going to be constant as well. So you can't use constant acceleration formulas here. We know the power. We know the length of the straight hill. Let's say it started from here, the car, and we want to find the speed at the top of the hill. It reaches this point eventually. The total length of this is 316. Okay. It takes 15 seconds to reach that highest point. Work done against resistance is given, that is 128,400. You've got power given. We've got the angle sine theta is 1/60. That's all the information that we have. Given that the car is traveling at a speed of 20 meters per second at the bottom, so at the speed at this point is 20 meters per second, find the speed at the top of the hill. We want to find the speed at the top of the hill. It's a classic case of work energy principle, right? We've got work done against resistance. We've got the speeds. We have the change in height. We can find that, right? So change in potential energy, change in kinetic energy, work done against resistance. What does that remind you of? The work energy principle. Work done by the driving force, that equals change in kinetic energy plus the change in potential energy plus work done against resistance. We just have to input values in this. All right. We just have to input values in this. Okay. Now, power is this. This is 16,000 watt. We know the time taken. Do we have a power formula that has time? Power equals work done over time. What we can do is we can find the work done by the driving force using that. Power is 16,000. Work done over time, that's 15. That will give you the work done by the driving force. What does that turn out to be? 24,000, right? That's 240,000. That's the work done by the driving force. Now you just have to input values in this. Work done by the driving force is 240,000. Change in kinetic energy is half into m. What's m? M is m. Do we have the mass? 1200. 1200, it was given in the previous part, into V squared minus 20 squared. That's the change in kinetic energy. Change in potential energy, mgh, m is 1200 into g, that is 10. Change in height. We want the change in vertical height. Let's call this h. Can we find this h? We are given sine theta. We know the hypotenuse. We can use sine here. We can say h over 316 equals sine of theta. And that will give us the value of h, which is 316 over 60. What does that simplify to? The value for h, what does that simplify to? Three one six over 60, 79 over 15. Okay, so h turns out to be 79 over 15. Right, so basically we just input 1 over 60 there. We know that sine theta is 1 over 60, so we input that there. Okay, so now mgh, that becomes 79 over 15. We keep this positive because the height is also increasing. Height is increasing, so this number is supposed to be positive. Plus the work done against resistance, that's given 128,400. And that is going to give you the value for V. Just solve this equation. That's 6 marks, a lot of marks just for this. Because this is the last question as well. That's supposed to be difficult generally. 240,000 equals 600 V squared minus 400 into 600. Just be careful with your working. Don't do any careless errors. Minus 240,000 plus 12,000 into 79 divided by 15. That's 63200 plus 128,400. And that will give you the value for V. You can see what that is. 21.9. So V equals 21.9. That's the final answer that you would get from this. That's the speed at the top of the hill. Yes, so when they say steady speed, if it's a horizontal surface and there is no other force acting apart from the driving force and resistance, then you can say driving force and resistance are equal. If there are any other forces as well, then you also have to consider them. If driving force and resistance are the only forces, then yes, in steady speed case, they will be equal to each other because the acceleration is 0. Then if you also have friction, generally, when they talk about resistance, friction is already going to be a part of that. So they won't say friction separately and resistance separately. There could be some other force. Whatever the forces are, if the acceleration is 0, if it's steady speed, what that means is the forward forces and the backward forces, they should be equal to each other. So it's like equilibrium. It's dynamic equilibrium when the object is moving, but still it's an equilibrium because the forces acting in opposite directions, they're equal to each other. So you would just equate the opposite forces. Okay. Acha. In question 6, part A, the left side was greater than the right side, that Q was more than P. Then how would we write that in the final comment to conclude? Just like this, 6A, we just said this. 1.732 is greater than 1.216. We just write this inequality. So that's why the particles start moving. Right? So we just say that number is greater than the other number. That's it. Whatever forces you have in that case of the Nadi, whatever forces you have, the opposite forces will be equal, like equilibrium, right? Whatever forces you have acting on the right side, acting towards right side, and whatever forces you have acting towards the left side, we would just equate those forces. Okay, just equate those forces, and that's it. That's this paper. That was paper 4.1. AB is smooth because, okay, so the question is, how do we know that AB is smooth in the second part of this question? Because they mentioned that AB is smooth in the main question statement. So that is relevant. That is relevant for the next part as well. That's relevant for both parts. So when they say the plane AB is smooth, that is true for the whole question. Yeah, it happens sometimes. How to avoid burnout? अभी तो एग्जाम शुरू भी नहीं हुए, अभी थोड़ा पढ़ लें. Don't make excuses that you'll have burnout and stop studying at this point. Next week जब शुरू होंगे, then think about it. Okay, so that was 4-1. Okay, now the next paper that you want to do is paper 4-3. I just need a few minutes break, then we do that next paper. From this paper, you are basically telling me that you want to do questions 5, 6, and 7, right? So from this paper, we will be solving questions 5, 6, and 7 now, inshallah. Okay, but just a few minutes break, 4-5 minutes, and then we resume. Okay, let's resume. Paper 4.3, this is the next paper that we're doing. ये आपके साथ जो है वो बचपन से एक मजाक हुआ है, एक प्रैंक हुआ है। आपको बचपन से सबने यही कहा होगा कि ये कर लें और आगे आसान है, ये ऐसे ही चलेगा। अनफॉर्चुनेटली अभी आपको हम कहेंगे ए लेवल्स आसान है, उसके बाद जिंदगी जो है वो बहुत आसान है। भी आप यूनिवर्सिटी जाएंगे, फिर आप यूनिवर्सिटी में कहेंगे यूनिवर्सिटी बस आप ग्रेजुएट कर लें, देन इट्स फेयरली स्ट्रेट, उसके बाद जो है सब कुछ आसान है। फिर आप जाएंगे, जॉब करेंगे, फिर आप जो है शादी होगी आपकी, फिर सुकून नहीं आएगा आपकी जिंदगी में। एज इमरान खान से सुकून है सिर्फ, सुकून सिर्फ कब्र में है। होपफुली अल्लाह करे वहां पे हो, जिंदगी में नहीं है। ओके, क्वेश्चन नंबर नहीं, क्वेश्चन नंबर नहीं, नेक्स्ट पेपर, मई जून 2023। जी बिल्कुल ऐसे ही है। ओके अच्छा, नहीं, नो पॉलिटिकल टॉक्स है प्लीज, सारे जो है वो, कोई फायदा नहीं है किसी का भी यहाँ पे। ओके, लेट्स स्टार्ट विद दिस। अच्छा नहीं प्लीज, नो irrelevant टॉक ना, बस खत्म, लेट्स रिज्यूम। May June 2023, paper 4, reading 3. Let's have a look at some questions from this paper now. इससे आपने कहा questions 5, 6, and 7, right? Let's have a look at these questions. Question number 5, 6, and 7. Okay. A particle starts from rest from a point O and moves in a straight line. The acceleration of the particle at time t seconds after leaving O is a meters per second square, where a is equal to this. For time between 0 and 9, where k is a constant, the velocity of the particle at time t equals 9 is 1.8 meters per second. Show that k is equal to 0.1. अच्छा, आपके पास you have an acceleration function, and that acceleration function is kt raised to the power 1 over 2, where time is between 0 and 9. Now it starts from rest at O, starts from rest. And we're given that the velocity of the particle at time 9 is 1.8. How do you go from acceleration to velocity? How do you go from acceleration to velocity? You integrate it. Let's integrate. K remains as it is, t raised to power 3 over 2 divided by 3 over 2 plus c. Okay, now you have to find the value of c somehow. Put t equals 9 for that. No, we have to show that, or is that given? Okay, that's given. We are given that t is equal to 9 when velocity is 1.8. That's 1 point that we have. So we can, and another point is when time is 0, at that point, the velocity is 0, because it starts from rest. That means when time is 0, velocity is 0, and when time is 9, velocity is 1.8. Let's start with that first of all. When time is 0, let's input v equal to 0. What do we get from that? That's going to give us c equal to 0. So c gets eliminated because the value of c turns out to be 0. What are we left? What are we left with? This 2 goes to the numerator and it becomes 2k t raised to power 3 over 2 divided by 3. Now we put the other point. We put t equal to 9 and v equal to 1.8. And that gives us 1.8 equal to 2k over 3 into 9 raised to power 3 over 2. And you can see what this turns out to be. 3 gets multiplied on the other side, 1.8 times 3. 18 times 3 is 54, so that's 5.4 divided by 2. That will become 2.7. 2.7 equals k into 9 raised to power 3 over 2. 9 raised to power 3 over 2, what's that? 3 cubed, that's 27. And k turns out to be 2.7 over 27, that is 0.1. That's what you had to find out. That's the first part. Okay. That's pretty straightforward. Part A. Now it says, for t greater than 9, the velocity of the particle is given by this function. Show that the distance traveled in the first 9 seconds is 1/10 of the distance traveled between time equals 9 to time equals 18. Okay, now what's the velocity function for the first 9 seconds? Velocity function for the first 9 seconds, that is 2k t raised to power 3 over 2 divided by 3. Now we know the value for k, so we can input that value of k here. K is 0.1. Let's input that in place of k here. 2 into 0.1. So it becomes 0.2 over 3 or 1 over 15. 1 over 15 t raised to power 3 over 2. Just put this on a calculator. 0.2 divided by 3, that gives you 1 over 15. So we write integers instead of decimals here. 1 over 15 into t raised to power 3 over 2. That's the velocity function for the first 9 seconds. Now, you can check for change in direction because we have to find distance traveled. When you have to find distance traveled, we always check if the direction changes at any point. In this case, if you put v equal to 0, you only get t equal to 0 from that. That means there's no change in direction. Okay. In the first 9 seconds, there's no change in direction. So you can directly integrate this and input the limits. What's the displacement going to be? 1 over 15 as it is into t raised to power 5 over 2 divided by 5 over 2. Input limits from 0 to 9. Can we simplify anything? We can take 2 to the numerator and it becomes 2 over 75 into t raised to power 5 over 2. Now you can input these limits from 0 to 9 and see what that gives us. We have more space to answer. So we have 2 over 75 into 9 raised to power 5 over 2 minus 2 over 75 into 0 raised to power 5 over 2. Now we can simplify this and see what that gives us. 3 raised to power 5 into 2 divided by 75. That's giving me 162 over 25. Can somebody confirm this as well? That's what we get, right? 6.48. That's the distance traveled in the first 9 seconds. How do we know that direction does not change? How do we check for change in direction? We put v equal to 0. You should do that here. Put v equal to 0 and see what that gives you. When you put v equal to 0, the only value of t that you get from that is t equal to 0. Right? When you put v equal to 0, you get t equal to 0. That means there's no change in direction. Okay? Between 0 and 9 seconds, there's no change in direction. Then you have the other function that is valid from 9 onward. If we got another value of t when velocity was 0, then we'll have to break the journey into 2 parts. So let's suppose we got t equal to 6 from that. Then we would have to input limits from 0 to 6 separately and then 6 to 9 separately. We could not do that together. Okay, you have to break down the journey. Okay, now what about the second part of the journey? It's when time is greater than 9. The velocity function that we have here is v equals 0.2 into t minus 9 whole squared plus 1.8. Is the direction changing here? Again, you should check that. Put v equal to 0 and see what that gives you. 0 equals 0.2 into t minus 9 whole squared plus 1.8. 1.8 will go to the other side, become negative, and that equation cannot be solved because on the right side we have a square. A square can never be negative. So this does not give us any solution. So that means the direction does not change after 9 seconds as well. So again, we just integrate this part as well now. What's the velocity function? The velocity function is 0.2 into t minus 9 raised to power 2 plus 1.8. Integrate this. 0.2 remains as it is. Add 1 to the power. So t minus 9 raised to power 3. Divide by the new power. Divide by the derivative of t, which is 1. Integration of 1.8, that's 1.8 times t. Input limits from what? 9 to 18. Okay, so 9 to 18. These are the end limits that you input here. Let's see what we get from this. 0.2 into 18 minus 9 raised to power 3 divided by 3 plus 1.8 into 18. Subtract from this the case when you input t equal to 9. That makes the first term 0 and the second term 1.8 into 9. Now you can simplify this and see what this turns out to be. What do we get from this? (324/5), which in decimals would be 64.8, right? 64.8. Now you just add them up together. Total distance traveled. And see what that turns out to be. 6.48 plus 64.8. What's that? 71.28. This is an exact number, so you can just write down the whole thing. And that's your final answer. That's the distance traveled. Whenever you have to find distance traveled, you have to check for change in direction. If they're asking you for the displacement, in that case, you don't have to check for change in direction. You can just directly input limits. Or if they want you to find out distance between 2 points, in that case as well, you do not have to check for any change in direction. You can just input limits directly in that. But when they ask for distance traveled, in this case, it's necessary that you do check for change in direction. Okay, let's move on. Part C of this. Now it says find the greatest acceleration of the particle during the first 10 seconds of its motion. Now, what's the acceleration function? The acceleration function is kt raised to power 1/2. The value for k was 0.1. So that's 0.1 t raised to power 1/2. Zero 0.1 t raised to power 1/2. Okay. We want the greatest acceleration during the first 10 seconds of the motion. That means we also have to check, because this is only valid for time 0 to 9. Look at the question again. Okay, so this first equation is only valid for time between 0 and 9, but they're asking us to find the greatest acceleration during the first 10 seconds. We'll have to consider the second part of the journey as well. That's greater than 9. We'll have to consider that separately. Now, this is the acceleration function. How do you find greatest value of anything? Greatest value of anything. How do you find that? Any function. Maximum value or minimum value. V equal to 0. Why? Whatever the function is, you differentiate that and put that equal to 0. Derivative of a is not v, it's something else. dA over dt. What will that be? 0.1 into 1 over 2 into t raised to power minus 1 over 2. Put this equal to 0, and that gives us 0 equals 0.1 over 2t raised to power 1 over 2. And that does not give us anything. Right? T will go there, get eliminated, and we get 0 equal to 0.1. That does not make sense. There are no solutions from this. So for the first 9 seconds, we don't get any value for that. So we have to consider what happens after the first 9 seconds then. Now, after the first 9 seconds, we are given that this is the velocity function, right? Now, what's the velocity function? We've already found the derivative of that before, have we? No. Now, for the next 1 second, the velocity function is 0.2 into t minus 9. 0.2 into t minus 9 whole squared plus 1.8. That is the velocity function. Now, how do you find the acceleration function from this? You differentiate this. 0.2 into 2 multiplied by the power, subtract 1 from the power, and multiply by the derivative of what is inside. Oh, okay. Okay, let me go back to that question. Okay, sorry about that. We'll go back to that part, the previous part. A is equal to 0.2 into 2 into t minus 9. Let's simplify this. That gives us 0.4 into t minus 9. Now we put this, we find the derivative of this. We find the derivative of this, dA over dt. That turns out to be 0.4 into 1, which is the 0.4. Okay. So what that tells us is the acceleration. So we'll have to do it without differentiation then, because this is not giving us anything. Okay, let's do it without that, and then we'll see if we could do something else. Okay, so let's think about it without differentiation, and then we'll see if there's another way to do this. So since this is not giving you anything as well, right? Because this will become no solution as well. The first function is 0.1 into t raised to power 1 over 2. The first function, when will it have its greatest value? When t is the greatest. In this interval 0 to 9, the maximum possible value of t that we can have is 9. Find the value of a at t equals 9 and see what that gives you first. That gives you 0.1 into 9 raised to power 1 over 2, and this gives me 0.3. So from the first function, the maximum acceleration would be when t is highest, right? When t is the highest value, then acceleration would also be the highest. So from 0 to 9, the maximum value of a that we're getting is 0.3. And what happens after that? After that, this is the acceleration function that we've got, 0.4 into t minus 9. And this turns out to be 0.4 t minus 9 into 0.4. What's that? 3.6. 0.4 t minus 3.6, that equals 0. Now it's a straight line. It's a straight line with positive gradient. So from 9 to 10 now, from t equal 9 to 10, when will we have the greatest possible value for acceleration? When we'll have the greatest possible value for acceleration in this interval? When t is the highest, because it's a straight line, right? The line is like this. So as we go to the right side, acceleration will also become bigger. So from this equation, when we input t equals 10, that is going to give us the maximum acceleration. Let's see what this value turns out to be. This turns out to be 0.4 into into 10 minus 3.6. And that gives us 4 minus 3.6, that's 0.4. The maximum value from the second part of the journey is greater than 0.3 from the first part. So we can say this is the greatest possible acceleration. Differentiation is not working here because this is a straight line function. It does not have a maximum value as such. So we just think of the straight line and we have the maximum point at the extreme right. For the first function as well, it does not have any turning point. It's a square root function. Its graph actually looks like this. This also does not have a turning point. So when we put the derivative equal to 0, that does not give us any solution, because that's what we generally do otherwise, that we find the maximum minimum points using differentiation. In this case, that doesn't work because these functions do not even have any turning points. So we just have to think of it logically. When will the first function give you the highest value? You have 0.1 into t raised to power something. 0.1 is a constant. This value will be big when t is big. So what's the largest possible value of t that we can have? This function is only valid from 0 to 9 seconds. So in that time interval, the maximum value of t that we can have is 0.9. So we check what the acceleration turns out to be at 0.9. That's 0.3. Similarly, in the second part of the journey, we check the acceleration at the highest value of t, which is 10 here, and that turns out to be 0.4. So that is supposed to be the maximum possible acceleration that we get from this. Does that make sense? Differentiation doesn't work. Otherwise, generally we use differentiation in such problems. But in this case, that does not work because the functions do not have any turning points. Does this make sense? Highest मतलब कम भी हो सकती है. What do you mean by कम भी हो सकती है? I don't understand what you mean by that. Okay. So let me repeat. We have two acceleration functions. One from time 0 to 9. This is the first acceleration function. From time greater than 9, we got another acceleration function. We want to find the maximum possible value of acceleration. We want to find the maximum possible value of acceleration. How do you find maximum value of any function generally? How do you find maximum value of any function generally? You differentiate that, put that derivative equal to 0. That's what you generally do, right? But in this case, these functions do not have any turning points. The first function, when we try to find the turning point, does not have any. The second is a straight line. Straight lines don't have any turning points. So differentiation doesn't work. So we just think of it logically then, that when would these functions have the greatest possible values within the given values for t, within the possible values for t. So the function is a equal to 0.1 t raised to power 1 over 2. That's the function. The greater the value of this t is, the greater the acceleration would be, right? Because 0.1 is getting multiplied by t. So as t increases, the value of a would also increase. Within this interval, what's the largest possible value of t? That's 9. So that's why we put 9 there. Similarly, in the second part of the journey as well, as t gets bigger, the acceleration also gets bigger. So what's the largest possible value of t that we have in this interval? Since we are only looking at the first 10 seconds of the motion, the time interval that we have in the second part is just from 9 to 10. So we put the largest possible value of time in this interval, that's 10. And that gives us this acceleration 0.4. That means this is the greatest acceleration. All right. Okay, good. Let's move on. That was quite different. I haven't seen any other question like this before in any past papers. Okay, question number 6. An elevator is pulled vertically upwards by a cable. What's that? Actually, we have to draw a graph. I was just thinking, why is it blank? Okay. An elevator is pulled vertically upwards by a cable. The elevator accelerates at 0.4 meters per second squared for 5 seconds and then travels at a constant speed of for 25 seconds. The elevator then decelerates at 0.2 meters per second squared until it comes to rest. Find the greatest speed of the elevator and hence draw a velocity time graph for the motion of the elevator. Okay, now it's accelerating initially at 0.4. So let's consider the first part of the motion. For the previous question, if you do not show this differentiation, that's also going to be fine, because you could actually judge from the function itself. If you know the graph of the square root function, it looks like this. It does not have a turning point. So you could just not show this working at all, and that will be okay. So without showing this differentiation working as well, you would get full marks as long as you've shown this working here. And of course, you found the function for acceleration using differentiation. Okay, now we've got an elevator and for which the acceleration is 0.4 for 5 seconds. Okay, so it accelerates at this constant acceleration for 5 seconds and then travels at constant speed for 25 seconds. Then it decelerates at 0.2 meters per second until it comes to rest. Find the greatest speed of the elevator and hence draw velocity time graph for the motion. Okay, now it doesn't explicitly say that here, but I think we can assume that the initial velocity is 0, right? Because it's being pulled up, right? It's being pulled up. That means it starts from rest, right? Starts from rest. Although it doesn't explicitly mention that here, but it's being pulled vertically by a cable. It accelerates at this acceleration for 5 seconds. And we're not given anything before this, so we can assume that it starts from rest. So initial velocity is 0. Then what's the final speed going to be? V equals u plus at. V equals 0 plus 0.4 times 5. And that turns out to be 2 meters per second. And now we have to draw a velocity time graph. What would that look like? It's going to be straight lines because we've got constant acceleration. And let's draw x and y axes like this here. This is velocity. This is time on the horizontal axis. Okay. Now, what are the important points? It starts from at time 0. It accelerates for 5 seconds. We can put 5 here. Then it travels at constant speed for 25 seconds. So we can mark 30 here somewhere. And then it comes to rest. At some point, we don't know at what point it comes to rest. Let's just mark it anywhere. It accelerates constantly in the beginning. It accelerates constantly in the beginning. So we can have a straight line for that part. We know that this velocity value is what? 2. This is meter per second. This is seconds. And then it remains at constant velocity for 25 seconds. That means up to 30 seconds. Okay. And then it comes down. Now for the last part of the journey, we're given the deceleration. Can we figure out that point at which it comes to rest? Let's consider the last part of the journey. For the last part of the journey now, we know the initial velocity, that will be 2. I'm considering this part when it's decelerating. We know the acceleration. Deceleration is 0.2, right? So acceleration will be negative 0.2. And we know the, what else do we know? It comes to rest. We know the final velocity. V is equal to 0. And we can find the time taken for this. V equals u plus 80. Again, we can use that. And that gives us 0 equals 2 minus 0.2 times t. And the value of t turns out to be 2 over 0.2, which is 10. So it takes 10 seconds to decelerate. That means this number here, 30 plus 10, that is supposed to be 40. That is what the velocity time graph is going to look like. Is that okay? Any issues with this? No? All right, let's move on. Find the total distance traveled by the elevator. Now you have a velocity time graph. You can just use that. Find the area of the trapezium. Half into sum of parallel sides. The base is 40. The side that's on top, that is 25 into height, that is 2, and that will give you the result. That's 65 meters. And that's the second part. Now it says the mass of the elevator is 1200 kilograms, and there's a crate of mass mkg resting on the floor of the elevator. Given that the tension in the cable when the elevator is decelerating is 12,250 Newton, find the value of M. Okay, now how do we think about this? We can draw a diagram. We can say this is the elevator. Inside the elevator, we have a crate of mass that is of n kilograms. This is n kg. Given that the tension in the cable when the elevator is decelerating is 12250. Tension, where would that be? So the cable will be connected on top, right? So tension will be acting in this direction. They're saying this tension is 12,250. That's the value of tension that we've got. Okay. What other forces do we have acting here? We have weight. What's the total weight of both of these? That will be acting in the downward direction. 12,000 for the elevator and 10 times m for that mass. We can say the total weight acting in the downward direction. That would be 12,000 plus 10 times m. So if we consider the whole system, both of them, when you have elevator and elevator questions, generally it's easier to consider the whole system first, right? So we consider the whole system because the box or the crate is inside the elevator. So we treat all of this as a single object, okay? We can make separate equations as well for the lift and the crate. That is possible, but they are a bit more confusing. It's a whole complete method that we need to learn. I'm not sure if all of you have done that or not. So elevator problems have a certain way of dealing with them. If you have not covered that, what you can do is you can search for elevator problems or elevator questions on my channel, and you would find that. The elevator problem, there's a separate video on that. It's around like 15-20 minutes, I think. You will, yes, in the mechanics playlist, that's the last video on that in which I've explained that whole concept. 36 minutes, okay, yeah. So you can use that to understand this whole concept. You saw that but did not see that. What does that mean? I get what you mean, but that's a confusing way to say that. But all right. We consider the whole system. We've got the downward force, that's 12,000 plus 10m minus this. Since which direction is the elevator moving in? It's moving vertically upwards. Okay, it's going upwards. It's going upwards. That means the forward force is 12,250. Subtract from that 12,010m. That equals mass. What's the mass? Mass is 1200 plus m into acceleration. Acceleration is what we have to find out, or what? Oh, we found the acceleration somewhere when it was decelerating. It was negative 0.2. We knew that it was given in the question. And that you can find the value of m from this. You can see what that is. 250 minus 10 times m equals minus 1200 plus m, because that's the total mass, right? We're considering the whole system. Considering the whole system, what's the total mass of the system? 1200 plus m. 250 minus 10m, that equals minus 240 minus 0.2 times m. 9.8 times m, that equals 490, and that will give you the result. You can see what that is. What do we get from this? 50 kilograms. That's the mass. We are just considering this whole system, and this the lift is moving in the upwards direction. Lift is moving in the upwards direction. Since the lift is moving in the upwards direction, what's the forward force? The forward force is 12,250. Backward force is 12,010 m, the weights of both of those objects. That equals mass into acceleration. We are considering the whole system, right? Both the lift and the mass together. What's the total mass? The total mass is 1200 plus m times acceleration. They asked us to find the tension, to find the mass when the elevator is decelerating. They told us earlier the elevator decelerates at 0.2 meters per second square. That's given in the question. So we are using 0.2 from there. Since it's deceleration, we use negative 0.2 as the value for acceleration there. Does that make sense? Okay, let's move on. Now it says, find the greatest magnitude of the force exerted on the crate by the floor of the elevator and state its direction. Okay, now again, think about this. We've got this elevator. There is a mass inside the elevator. Now, we're talking about the crate. So now we have to think from the perspective of the crate. What forces do we have acting on the crate? What forces do we have acting on the crate? There's weight of the crate that acts vertically downwards. That's 10 times m. There's normal reaction. Normal reaction, the reaction that the lift applies on that crate, that acts vertically upwards. Right? What other force do we have? These are the only forces that we've got. Okay. All right. Now they're saying, find the greatest magnitude of the force exerted on the crate by the floor. What does that mean? There are three parts of this journey. In one part of this journey, the lift is accelerating. If the lift is accelerating, that means the force that is being applied in the upwards direction is greater than the force that's acting in the downward direction. At that point, the lift will be accelerating, right? So when you think about, okay, sorry, that was not the diagram, the other one. Yeah. So there are three parts of the journey. In one part, the lift is accelerating. That means it's accelerating upwards. In one part, it's traveling at constant velocity. In one part, it's traveling, it's decelerating. When it's accelerating, remember resultant force equals mass into acceleration, right? What's the forward force? Forward force is R here if the lift is going up. Backward force, that is 10m. That should equal mass into acceleration. If we want to maximize R, that means lift should be accelerating. The value of A should be as big as possible. So when the lift is accelerating in the upwards direction, R is going to be bigger than 10m. When the lift is traveling at constant velocity, that would mean acceleration is 0. In that case, R would be equal to 10m if it was traveling at constant velocity in the middle 25 seconds. When the lift is decelerating, that means the downward force, that is 10m, that would be bigger and R would be smaller. Right? Then the value of acceleration would be negative if R is smaller. We want to find the greatest magnitude of the force exerted on the crate by the floor. That's basically this reaction, the greatest magnitude. When will that be? When the lift is accelerating upwards. This will be when the lift is accelerating. Now, what was the acceleration of the lift that we were given in the first part of the journey? 0.4 meters per second squared. That is what we use here. We say it becomes R minus 10 times m. We already know the value for m now. That's 50 equals 50 times 0.4. And that will give you the value for R. That's the greatest possible value of R. 20 plus 500, that's 520 Newton. That's the force that we get in this case. So you must have noticed when you are in a lift, when the lift starts moving upwards, you feel some force on your feet because the lift is accelerating at that point. But then when it has moved a certain distance, it has gone to the second, third floor, you don't feel that force anymore because at that point the speed becomes relatively constant. So you don't feel that force from the ground, from the lift anymore, right? And when you're going down, initially it looks like you feel lighter when the lift just starts going down, especially if the lift is not very good quality. You feel that more. If it's good quality, then you don't have that feeling generally. But that's what happens. When it's accelerating, the value of R is bigger. When it's decelerating, the value of R is smaller. Okay. All right, let's move on. Okay, I'll do that once. I'll do that. Let's look at question number 7 next. Okay, one last question. Okay, let's try to be a bit quick about this. Yeah, I'm sorry about that. Now it says the diagram shows the vertical cross section XYZ of a rough slide. The section YZ is a straight line of length 2 meters, inclined at an angle of alpha to the horizontal, and sine alpha is 0.28. The section YZ is tangential to the curved section XY. Okay, what that means is the direction of the curve at this point is the same as the direction of the straight line. So there's no change in direction at the point Y as such. That's what it means. We've got the distances. We can see all of that in the diagram. A child of mass 25 kg slides down the slide, starting at x. The work done by the child against the resistance force and moving from x to y is 50 joules, work done against resistance. Find the speed of the child at y. How do we do that? We can use work energy principle, right? No, it's not like that. It's all right. I actually started late. My P1 class started late, and then this also ended up being late. So it's because of that. Find the speed of the child at y. How do we do that? Work done by the driving force, that equals change in kinetic energy plus the change in potential energy plus the work done against resistance. What's the work done by the driving force? There's no driving force, right? The child is just going down because of his or her weight. So there's no driving force. Change in kinetic energy, it start from rest, and then we don't know the final speed. Let's say that this is v meters per second. That will be half into m, which is 25, into v squared minus 0 squared, plus the change in potential energy. M is 25 into g, that is 10, into change in height. What's the change in height? What's the change in height? Yes, it doesn't matter. You can use this for curved motion, for straight line motion. That does not matter. When it's a curve, you never use constant acceleration formulas. When it's a curve, acceleration changes at every single point. You never use constant acceleration formulas in a curve. But this always works. The inner work energy principle always works. 25 to 10. Now this value, change in height, will be negative. It's a potential energy is decreasing. So the change in potential energy is supposed to be negative. So we will consider this a negative change in height. That's negative 1.8. Work done against resistance, that's 50 joules. And that will give you the value for V. You can see what that is. What do we get from this? 4 under root 2, and that's it. That's your final answer. You can write this in decimals or just leave it like this, and that will be okay. All right, part B. That's the last part. Okay. It's given that the child comes to rest at Z. At Z now, the child comes to rest. His speed becomes 0 meter per second. Use an energy method, again, that work energy principle, to find the coefficient of friction between the child and YZ, giving an answer as a fraction in its simplest form. Okay. Now, we have already found the speed at the point V now, right? We know the speed at the point V. What's that? That's 4 under root 2. So this is 4 under root 2 now. Let me write that here. 4 under root 2 meters per second. What we have to find out is, in fact, we know the final speed as well. Okay. Now, what about the change in height? So we can find the change in kinetic energy from this, right? We have the speeds. Can we find the change in height as well? We'll use that to find the change in potential energy. We can make this right angle triangle. We are given that sine of alpha is 0.28. Let's find this value for h. H over 2, that equals sine of alpha. H equals 2 into 0.28, and that is 0.56. This value is 0.56. That's the change in height. Okay. So we can find the change in potential energy from this. Is there any driving force? There is no driving force. We just have work done against resistance left. We can find that. Let's see what that turns out to be. Work done by the driving force, that equals change in kinetic energy plus the change in potential energy plus work done against resistance. There's no driving force, so there's no work done by the driving force. Change in kinetic energy, half into m was 25, into final speed was 0, minus the initial speed, that was 4 under root 2. We're considering this part of the journey from y to z. 4 under root 2 squared. Okay. Plus change in potential energy, m, into g, into change in height. What's the change in height? 0.56, but that's also negative because it's decreasing. Minus 0.56 plus the work done against resistance. Can we find the work done against resistance from this? You'll get that value, right? Has anyone done that? 16 times 2 is 32. Divided by 2 into 25. That's 400 minus 400 into 0.56, 140 plus work done against resistance. Does it turn out to be 540? Can anyone confirm that? Is that 540 joules? Okay, that's the work done against resistance. Now that we've got the work done against resistance, we have to find the coefficient of friction. Now, what's work done against resistance? How is work defined? Work is force into displacement. Work done against resistance would be friction times the displacement. So we can say 540, that equals friction times displacement. What was that? 2 meters. And that will give you the value for friction. That is 270 Newton. Now we can use F equals mu r to find the value of coefficient of friction. F is 270 equals mu into r. What is r going to be now? You have to consider forces for that. Take any point, let's say this point. The weight of the child is going to be 250 Newton. Its component acting in this direction, that will be 250 cos alpha. So reaction is going to be equal to 250 cos alpha. These two values are going to be equal to each other. That's the value of r. We can say r is equal to 250 cos alpha. Now the question gave us the value for sine alpha. That was 0.2 something, 0.28. Can we find the value of cos alpha from that? Just put this on our calculator. Sine inverse of the answer. Sorry, sine inverse of 0.28. And you find cos of that. That's 0.96. Put that here. The value of r turns out to be 250 into 0.96. What's that? 250 into 0.96. That's 240. That's the value of r. Put that here. And that will give you the value for mu. Mu equals 270 over 240. That's 9 over 8. Or in decimals, that would be 1.125. That's the value of mu that we've got. And that's our final answer. Make sense? All right. Okay, now, just a minute. I'll just go back to one question. I forgot, Asha told me in the middle, but I then forgot about that. But what question was that? It was in the previous paper. So in the previous paper, we had a question in which we found, which paper was that? It was this paper? Okay. So in this paper, we had this. Okay. So question number 5, part B, they actually wanted us to show that the distance traveled in the first 9 seconds of the motion is 1/10 of the distance traveled between time equals 9 and time equals 18. They did not ask us for the total distance traveled. So when we found these two values, at the end we found total distance. That's not what the question asked. We did not have to do this. Instead, we just had to show that this number is 1/10 of this number. Right? How would you do that? You would just say 64.8 divided by 6.48. That gives us 10. And that shows that this number is 1/10 of that. So that's what you had to do at the end. Instead of saying total distance traveled, you had to show that the smaller value is 1/10 of the bigger value, like this. Okay. Abdurrafi, can you be specific about it? What particular part do you not understand from this? What exact concept? What do you not understand? Because if it's just about going over again, then you have the recording for that as well. So if you have a specific question, ask that question. Part C. What about part C? What's the actual confusion? Maybe you can ask verbally. Okay, by the way, those of you who want to leave, it's late now. Thank you so much. I'll see you again in the next class. We will end here. I'm just answering the Rafi's question. I'll see you again in the next one, inshallah. Allah Hafiz. Thank you. What we will do in the next class, the paper that is left from June 23, on Monday, we'll be doing June 23 paper 4.2. June 23 paper 4.2, inshallah. Okay, yeah, sure. All right. So go over this again. I'll be uploading this recording right away. And then if you have any questions, you can ask in the group, inshallah. Okay, all right, good. Thank you. Allah Hafiz, everyone. I'm sorry for ending so late, but that's what happens sometimes. Allah Hafiz.